Hello everyone, today we are going to discuss about the preload and structure, focusing on the axial direction of superconducting magnet especially. Today, we'll explain the support structures for superconducting magnet especially focusing on the axial direction preload and Belleville washer. Superconducting magnets, when operational as shown in the diagram on the right, experience axial shrinkage due to the Lorentz force and cooling. This force causes a displacement along the axis of the magnet. As a result, the magnet can become unstable. To compensate for this effect, it is common practice to apply a preload structure in the axial direction. This axial preload helps counteract the axial displacement and maintains the structural integrity and operational stability of the magnet. Typically, superconducting magnets are stabilized using either external tie rods or internal tubes to manage axial alignment. Using tie rods simplifies construction but has the disadvantage of occupying additional radial space. On the other hand, employing an inner tube, while more complex to manufacture, allows for a more compact design. In the inner tube structure of superconducting magnets, Belleville washers play a crucial role to prevent the mechanical problems. Consider a stacked arrangement of superconducting magnets as depicted in the left diagram. Belleville washers are arranged in such a way that they can be compressed by tightening screws in the movable parts of the assembly. This arrangement effectively turns the Belleville washers into a spring mechanism, allowing them to act like a spring and implement a specific spring constant. This configuration provides critical benefits. It helps maintain a precise mechanical tension within the assembly, essential for managing mechanical stresses and ensuring consistent magnetic field characteristics under the cryogenic operational conditions. Preload can be calculated as the product of the spring constant of Belleville washer and displacement. Let's consider a straightforward example to see how to calculate the preload on a superconducting magnet. As previously mentioned, superconducting magnets undergo contraction during the cooling process and further shrink due to the Lorentz force when current is applied. This results in a reduction in the distance between the magnet and the stainless steel pad bottom, specifically by 0.2532 mm, as indicated in the table on the lower right of the slide. Considering the safety factor and the configuration of Belleville washers, we can calculate that a total preload of 2,496 newtons. In today's lecture, we discussed on the types of axial preload which can prevent wobbling and specifically discussed the role of Belleville washers. Belleville washers allow us to design and apply a desired spring constant to magents. By carefully calculating the spring constant, we can ensure that the preload applied via these washers meets our specific requirements. The importance of this capability cannot be overstated, especially when it comes to protecting magnets. A well-designed preload structure is crucial for maintaining the integrity and functionality of the magnet system under various operational conditions. It helps to mitigate mechanical stresses and vibrations that could otherwise damage the magnets or affect their performance.